Okay guys, let's take a look at today's lesson. So we're going to be working on a different kind of proof. I know that sounds exciting, right? You're like, oh wow. So let's talk about the proofs that we know how to do. So we did proofs in geometry, right? We did those two column proofs. We know we've done that before. In the fall, we did trig proofs. We know how to do that, and we've done some kind of algebraic proofs here and there. This is a completely different method to prove things. This is called mathematical induction. Basically, it's proof by mathematical induction. So what is that? So it's actually a very specific process. Very specific. There are 3 steps every time. 3 steps. So let's go through them. So the first step, what we're doing in this type of proof, we show that whatever statement we're trying to prove is true for one item, for one thing, for n equals 1. We prove that it's true for that. Okay, then what we do is we take it, in step 2, we take it to a more general term. So now we're going to assume the statement is true for n equals k. So for any, so we proved it's true for 1. We're going to prove that it's true for any number, and this is significant. K is a positive integer. This type of proof that we're going to be doing only works with positive integers. We're not trying to prove it on the other side of the, to the negative side, just positive. So we show the statement is true for n equals 1. We assume the statement is true for n equals k. That's step 2. And then step 3, we prove the statement must be true for the next term, for k plus 1. And that's the process. Okay, so it's a bit abstract. So let's kind of walk through the first one. So what I do and what I want you to do is write, step 1. You have to do all 3 steps of the proof. And sometimes, and I'm not sometimes maybe all you can do is just step 1 and step 2. And then you're kind of like, oh my gosh, what do I do? So you need to, every step is worth points. So we write all the steps down. So step 1 is n equals 1. And that's what I do, so I remember what I'm doing every time. Step 1, n equals 1. So what I'm going to do is I'm going to rewrite this with a 1 in place of all the n's. So I'm going to do my summation. Instead of an n, I'm putting a 1. And over here, instead of n's, I'm putting a 1. Now what I do is I work each side out and show that they are equal. So if I'm doing the summation from 1 to 1 of I, that's just 1. And then this is 2 over, right? 1 plus 1 is 2, 2 over 2, it's 1, so that checks. Step 1 is done. So we pretty much should all be able to get step 1 without a problem. We just sub a 1 in and then show that it's true. Done. Step 2. This is for n equals 2. Oh, excuse me, n equals k. This is for n equals k. So now I'm going to go back and I'm going to, everywhere there's an n, I'm going to place a k in there. So we have the summation from I equals 1 to k of I equals k times k plus 1 over 2. Now we have a little bit more work to do here. Because of the nature of what we have a summation. We can't really do any calculations. These are really, for the most part, algebraic proofs. We're going to be doing algebra during these proofs. And I really can't do any algebra with it all bundled up in the summation formula. I'm going to have to expand it out. So let's expand it out. So this would be 1 plus 2 plus 3 plus ... plus. And then we have, we go up to k, so plus k equals. And then on the other side, we just have our k times k plus 1 over 2. Okay, so that's my step 2. So step 2, we substitute a k in place of n. And if there's like a summation or anything like that, we expand it out. Okay? So step 3. This is where we do n equals k plus 1. So again, I'm going to go back to this original thing that's going on right here. Back to this original expression, and I'm going to put, everywhere there's an n, I'm going to put a k plus 1 there. Alright, so we have the summation from 1 to k plus 1 of I equals k plus 1 times k plus 1 plus 1 all over 2. Alright, we okay? So I'm going to take that left side, that summation side, I'm going to expand it out, you know, like I expanded the other side out. So this would be 1 plus 2 plus 3 plus dot 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 plus k plus 1. Okay, and that equals k plus 1 times k plus 2 over 2. Okay, are we okay? So hopefully we can all get that far, right? Where it gets a little tricky is the very last steps where we're actually doing the proof part, where we're proving. We've kind of set up the structure. The structure is the same every single time. You substitute, you do the n equal 1 step and show that it works for 1. You do the n equals k step and you sub in k, and then you do the n equals k plus 1 and sub in k plus 1. We should all be able to do that without a problem, right? The next step is where it gets tricky. Generally, I will tell you 80% or more of the time, you are going to be using something from step 2 to insert into step 3. Okay? The vast majority of the time. I would say more than 80%. The vast majority of the time. So what I would like for you to do is to kind of look at this portion right here and see if you can identify that in the step 3. Do you see that part? Okay, this part right here. So what I'm going to do is I'm going to use an algebraic property of substitution. I'm going to take all of this out and I'm going to substitute this in its place. We've just established these are equal to each other. So I'm going to take all of this out and put this in its place. Does that make sense? So let's do that. So this becomes k times k plus 1 over 2 plus k plus 1 equals k plus 1, k plus 2 over 2. Now let's talk about what we can and can't do on either side of our equal sign. So just like the proofs in trig proofs, remember where we just didn't touch one side? Remember that? This side, we can change the way it looks. I'm allowed to multiply this out or, you know, do stuff like that, but I can't add or subtract across this equal sign. That's not a thing. Okay, we're not going to be doing adding and subtracting across the equal sign. We're just going to, we can change the way it looks. What we want is these two sides to turn out to be exactly the same. Okay, so that means I'm going to have to find a common denominator and add these together, right? This is just one fraction, so I need to do that. So the common denominator actually would be 2, right? So let's just kind of sneak that in there. And let's distribute, let's add those fractions together by distributing combining like terms. Or let's just distribute first. So we have k squared plus k plus 2k plus 2 all over 2 equals. Now our choice here is, do we want to go factored or do we want to go foiling, multiplying everything out? It's really your choice. It doesn't matter to me. It's easier to multiply than divide, so I probably would go ahead and FOIL this side out over here. You know, do you have to? No, you could factor this side. It's really up to you. It's whatever you would like. They just have to match at the end. So I'm going to go ahead and FOIL this out. K squared plus, what do we get? 3k plus 2. And let's hope when I combine like terms over here, yeah, and I will. I'll get the same thing, won't I? I'll get k squared plus 3k plus 2 over 2 equals k squared plus 3k plus 2 over 2. Check. For those of my students that like to conserve energy, I'm sorry, there's very few places that we cannot write things. This is a proof and we have to write it all out. So sorry, it's just kind of the way it goes. Absolutely, absolutely. You don't have to FOIL this side. Instead, you could factor that side, and that's fine. It's totally up to you, whichever way you want to do it. Okay? So how are we with our very first mathematical induction? Are we okay? Yes? So we are doing it for the k plus 1 term. And so what I did is I substituted k plus 1 in here, but I wanted to write the previous term, to be honest, so that it could match this.
So n minus 1 times k.
Right. Right. Exactly. Or that if we go backwards 1, we would have k. Right? And so that's what we're doing here. I went backwards 1 to have k. And you can go back as far as you want. Like you could do k minus 1 right here and k minus 2. I mean, you could keep going backwards, but it's really depends on what you want to do. Okay, is that okay? All right, anything else? All right, so we have a couple more on the next slide. I wish I would be able to show you one of every kind that you're ever going to see, but that would be pretty much impossible. We probably don't want to spend 5 or 6 days on mathematical induction, so we are going to kind of try to show you a little variety, and then you have more variety on your daily work to see. Okay? You're like, oh, yay, yay. All right. So let's look at the next one. We're going to prove this. So the typical thing that we see are summations. I mean, I'm showing you the most common types of mathematical inductions proofs that you'll see. You'll see summations that you got to prove. You'll see these weird looking expansion things that you need to prove, and then you'll see just kind of weird word kind of things going on. All right, so I've tried to do one of each kind. So this one is the expansion type. And so we're going to do the 3 steps as usual. So step 1, that's where n equals 1. So now this is where it kind of confuses students. We are just proving this for the number 1, for 1. Okay? I don't need, these are a bunch of different terms, right? I don't need these for just 1. Right? What do I need for 1? I just need to put a 1 in here. Are you with me? I just need to put a 1 in here for 1. I'm not proving it for 1, 2, 3, 4, 5, 6. I'm just working on 1 term. Okay, so that really troubles students. So why did you get rid of all that? Well, I didn't get rid of all that. I'm just doing 1. Okay? So, and you can probably tell what 1 is going to be by just looking at this. Right? I hope you can tell. See the correlation here. What 1 is going to be by just looking at these terms. Right, so I'm going to put a 1 in here. So in this part right here, so I have 1 over 1 times 1 plus 1 equals 1 over 1 plus 1. So this is, what, 1/2? Which isn't that what that is? Right? I mean, that's 1. I'm doing it for just the first term, 1. This is kind of like a summation, but not, see, it is. It's like a summation, but it's not written in summation form, is it? Could I write this in summation form? Sure. Sure, but they already have expanded it out for us. All right, so I have 1/2 equals 1/2. Check. First step done. Okay, so now step 2 for n equals k. So we don't have to go through the first problem that we did started with the summation, then we had to expand it. Right, this is already expanded. It's really a summation already expanded. So I'm just going to copy all this down and put k's where the n's are. That's all I need to do. All right, so we're just going to copy it all down. 1 over 1 plus 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus dot 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 plus 1 over k times k plus 1 equals k over k plus 1. Okay, that is my step 2, the n equals k step. Okay, so step 3. This is the n equals k plus 1 step. Okay, so we're going to write all this down with the k plus 1. And I'm going to still write this part. Right? I'm going to write this part and the k plus 1 part. Okay, I still want to write the k part. I'm just going to expand it and write one more term. I'm going to write the k plus 1 term. So I have 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus dot 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 plus 1 over k times k plus 1 plus, now here's the k plus 1, 1 over k plus 1 times k plus 1 plus 1 equals, the other side is k plus 1 over k plus 1 plus 1. Whew, we got to make those equal. Yay! All right. So let's see, what do? We look to step 2, right? We see what can we use from step 2, and like the majority of the time that's what's going to happen. What can we use for step 2 to substitute into step 3 so that it's actually workable? So let's investigate. I kind of would like to get rid of all this mess right here and turn it into that. Let's see if that's possible. Yep, we see that part right here. Right, I'm going to take this part out. I'm going to use my substitution rule. And I'm going to put that in place of it. Okay, so here's what we have. Then we have k over k plus 1 equals, oops, no, sorry, plus. So I'm just replacing that first little string of stuff. Plus 1 over k plus 1, k plus 2 equals k plus 1 over k plus 2. Okay. So again, we're really not allowed to touch this side. There's nothing to do over here anyway. I mean, I don't think we're tempted to do anything. We're going to have to work on this side. We need a common denominator. We need to add them together. Right, so the common denominator would be, what, k plus 2, right? K plus 2 times k plus 1. So I would need to multiply this by k plus 2 over k plus 2. So let's distribute across the top. Let's add those fractions together. So I have, what, k squared plus 2k plus 1 over k plus 2, k plus 1 equals k plus 1 over k plus 2. Okay. Now, we really are not supposed to multiply this side by any form of 1. We're supposed to leave it alone. So let's kind of take that out of our head. We don't want to mess with this side. So let's work on this side. What could we do you think, to make this side look like that? Factor. Exactly. Factor. We need to factor. We need to factor this, which does factor to k plus 1, k plus 1 over k plus 2, k plus 1 equals k plus 1 over k plus 2. And so we see what we can do. All right, we can cancel. And so now, voila, for the final step, k plus 1 over k plus 2 does in fact equal k plus 1 over k plus 2. Check. I like that check. A check is like, woo, we're done. Okay, we okay on that one? So very similar to the one that we did before, a little bit different. I'm trying to show you some few nuances. Number 3 is really different. 3 is really different. Okay, does everybody have what they need? I need this space back. Can I erase? Okay. So number 3 has like words. It's wanting us to prove that n squared plus 2n is a multiple of 3. Okay, that's kind of weird, right? But let's just do, I'll show you, it works. Let's do it. So step 1, n equals 1. So what I'm going to do is I'm going to substitute a 1 in this expression. So 1 cubed plus 2 times 1 equals multiple of 3. Just going to use the words multiple of 3. That's perfectly fine. So let's see if that's true. So 1 cubed, so that is 3. Is 3 a multiple of 3? Yes. Right? It is. Check. We know what multiples of 3s are, right? 3, 6, 9, that multiples of 3. All right, step 2. N equals k. So here we're going to replace n with k. So k cubed plus 2k is a multiple of 3. Okay, that's what we're assuming to be true. Really nothing we can do to that, right? That's it. That's what we're assuming to be true. Now let's go to step 3. Step 3, n equals k plus 1. Okay. So I'm going to, this isn't a summation one. I can't expand this one out. That's not the way this one works. I simply need to go back here and put a k plus 1 in place of the n. So I have k plus 1 cubed plus 2 times k plus 1 is multiple of 3. So we're looking at that. It's like, yeah, we know we're supposed to try to find somewhere that this can sub into, but I'm not seeing it the way it's written. So I'm going to have to multiply it all out. Now we just learned binomial expansion. We should all be able to expand this binomial quite easily, right? We shouldn't have to FOIL it out, you know, three things to FOIL out. We shouldn't, because this is cubed, and what are our binomial coefficients for that row? 1, 3, 3, 1, right? 1, 3, 3, 1. Okay, so 1, 3, 3, 1, and we can see the way it expands. So it would be k cubed plus 3k squared plus 3k plus 1. Isn't that a beautiful thing, rather than having to multiply all that out? See, there you go, the benefits of binomial theorem. So then let's keep going. So plus 2k plus 2 is multiple of 3. Okay, back to our original. We really are looking for this. We want to find this in here. You think we're going to be able to do that? I bet we will. So I'm just going to highlight the areas. So we're looking for this. Okay, so I see that one. Okay, there's that one. I have the k cubed. Do I have a 2k also? I do, don't I, right here? So what I'm going to do is I'm going to take these two out, and I'm going to replace it with multiple of 3. I'm using substitution. Okay? I'm going to replace those two terms with multiple of 3. So let's do that. So multiple of 3 plus, and let's write the rest of it down, 3k squared plus 3k, and then 1 plus 2 is 3, equals multiple of 3. So do you think if I add a multiple of 3 to a multiple of 3, I will get a multiple of 3? I mean, yeah, that's the thing, right? So how can I show, now I can't really make the leap yet. I think you can see we're really close. How can I show this is a multiple of 3? By factoring out the 3, right? By factoring out the 3, I can show that it's a multiple of 3. So I have multiple of 3 equals plus 3 times k squared plus k plus 1 equals multiple of 3. Okay, we're right there. Is this a multiple of 3? We all agree it is, right? So now I have multiple of 3 plus multiple of 3 equals multiple of 3, check. Okay, there we go. How is that? Is that okay? I know it's a little intense, but it's the same procedure, same structure over and over again. Right? Step 1, step 2, step 3, same thing.